Hello everyone, and welcome back to our section on area. We are going to discuss in this video definite integrals and net area as a follow-up to the limit of Riemann sums. We've introduced the definite integral in the previous video by saying that the limit of Riemann sums, so the limit as the number of subdivisions or the number of rectangles goes to infinity, of the sum of the area of these rectangles is equivalent and can be written as the integral from a to b of f of x dx. The original purpose of Riemann sums was to compute area between the x-axis and a given positive function that was assumed continuous. However, does this still hold true when the function is not positive throughout the interval? We're going to compute a definite integral using the limit of Riemann sums to verify this fact. So as you can see here, the definite integral from -1 to 1 means that the interval we are going to measure the Riemann sums on is from -1 to 1. The function, the integrand, 3x squared minus 1, is the function whose area we're going to be computing. So starting off with our typical three-step approach, our pattern, delta x represents the width of each of the subdivisions. So b minus a in this case will equal 2, 1 minus minus 1. So that's the size of the interval, and we're splitting it evenly into n rectangles. So 2 over n is the width of each subinterval and coincides with the width of each of the rectangles. According to our procedure, a plus k delta x represents the right-hand point of each subinterval, which are the points we'll be using to find the function's height, and hence the rectangle's heights as well. So a is -1 in this case, and adding k times delta x gives us xk values, -1 plus 2 over n times k. Our next step is to find the function's height above these points. So f calculated at xk is 3xk squared minus 1. We're just following the rule that the function is indicating. Now xk stands for -1 plus 2 over nk. So we're going to have to square this expression, which is a binomial, which is a binomial term, and that means foiling it out. So I've spared you a bit of the algebra here, but if we FOIL out that parentheses, correctly expand and collect like terms, we're going to find 12 over n squared k squared minus 12 over n times k plus 2. Of course, this expression does not look at all like the height of a rectangle. You have to remember that that is, in fact, what you're calculating. F at xk is the height of a rectangle. It's the kth rectangle. That coincides with the right-hand point of each of the subintervals. Delta x is the width of all these rectangles, and therefore, summing the base times the height gives us a sum from the first rectangle till the nth, where in my square brackets, my square parentheses, I have the function's height, or if you prefer the rectangle's heights, times 2 over n, the rectangle's width. Distributing 2 over n to each of the terms and collecting constants with constants and n's with n's, we then have the sum of 24 over n cubed k squared minus 24 over n squared k plus 4 over n. And this is to be summed for values of k going from 1 to n. Remember your properties that allow you to split summations of added or subtracted terms into individual sums, and you're allowed to extract anything that is not a k term because that is the summation variable. So all constants, 24 over n cubed, 24 over n squared, and 4 over n can be extracted. Those three sums fall into place when we remember that we have formulas that allow us to calculate the sums of powers of k. The sums of k squares are replaced by the expression n plus 1, 2n plus 1 over 6. the sum of k and n plus 1 over 2. And if we add a bunch of ones, we'll have a total that is equivalent to how many ones we have, which is actually n of them. As I did in the previous video, here I've collected the numbers and the numbers to simplify them. So 24 over 6 is 4, 24 over 2 is 12. And I've distributed the n's and shared them to, or I've distributed the n cube, or the n's that are at the denominator, to the expressions that hold n's on the numerator. So the n cube is still there, but distributed into 3 pieces, and same for the n square, which I can then divide term by term to simplify our expression. Again, the reason for doing this is that it makes the limit process much easier when we realize that 1 over n will become 0 as n goes to infinity. So for now, this is a general expression that represents the Riemann sum when n rectangles are being used with also the right-hand points of each subinterval. Now, the limit of the Riemann sum will always give the same outcome regardless of the choice we made of points. In this case, the limit as n goes to infinity cancels off all of the 1 over n terms, which leaves a result of 0. And that should be quite surprising because in the past, all of our outcomes represented the area that was found between a function and the x-axis between bounds a and b. So how is it possible that 0 will be the outcome here, and yet that is the answer we've obtained? The definite integral between minus 1 and 1 of the function 3x squared minus 1 is 0. The answer is not as surprising once we take a look at the graph of the function. So here is a graph of the parabola y equals 3x squared minus 1. You'll notice that there is a portion of the area that is above the x-axis, and there is a portion of the area that is below. Now, although area is always a positive quantity, the integral actually adds the area above the x-axis and then subtracts from that the area that is below the x-axis. And that will result in this example with an answer of 0, which means there was actually the equal amounts of area above and below the x-axis. So the outcome is what we're going to call the net area. So from now on, we'll have to remember that the limit of Riemann sums, or if you prefer, the definite integral of a to b for the function f of x dx, is actually the total area between the function and the x-axis when f is positive, from which we subtract the total area between the function and the x-axis when f is negative, all the while staying between the interval a to b. For instance, when we integrate from minus 1 to 1, from minus a half to 1, the function ln of x dx, we will get a result that is negative, so roughly minus 0.153, which is not surprising because a logarithmic function is negative before getting to its x-intercept at 1. The integral from 1 to 2 of ln of x is roughly 0.386, a positive number, also not surprising because a logarithmic function is positive once x is beyond 1. If the integral had as its bounds 1/2 and 2, then the outcome would have been roughly 0.233, which is actually the difference, or the net result, between the area under the axis left of 1 and the area above the x-axis to the right of 1. It's actually the difference between 386, or 0.386, and 0.153. That would be the net area.